Today, we want to look at the average value problem that we talked about yesterday. From point A to point B, our average speed is 70 miles per hour. And then from point B to point A, our average speed is 50 miles per hour. My question was, what was our average speed and why is it not 60? So the first thing we notice is that the average of the speeds is 60. But that's not the average speed. That's not the same as the average speed. Imagine we had a test and out of 20 people, 19 people got a 50 and one person got a 70. The two scores that happened were 50 and 70, and the average of those scores is 60, but that is not the average score. We know that the average score is going to be much lower than that because there were a lot more 50 than there was 70. The same thing happens in this problem. What we're going to notice is that there's a 50 and a 70, but they don't carry the equal weight. They don't carry equal weight. Given the example I just had, think about what is the weight that each one of these has. Let's look at this algebra style and find out. So one thing to notice is that we don't know the distance from point A to point B, but that doesn't matter because it's the same from point A to point B and then from point B to point A. And what we're going to use is just distance is equal to rate times time. We don't know the distance, but we can fix it at some value. We can actually pick any value that we want, but I'm going to say let's let the distance between from A to B equal capital D. Capital D for distance. We can actually pick any value that we want. Because it doesn't matter how far it is from A to B. So if distance is equal to rate times time, the time we spent on that first trip, well, we could solve this. We could rewrite distance is equal to rate times time as time is equal to distance divided by rate. So the time we spent going from point A to point B is the distance D divided by the rate 70. And let's let T2 be the time that we spent from B to A. And that will just be D divided by 50. And right away, we see that we're not going to find the average of 50 and 70 because they have different weights. Distance is equal to rate times time. So the rates are different, but they're not weighted equally because since the distance is the same, the times are going to be different. In particular, the time spent going 70 miles per hour will be less. Let's find that out. We now are expecting a value less than 60. So the average speed is the total distance divided by the total amount of time. We went from point A to point B, that's a distance of D. We went back from point B back to point A, that's a distance of D again. So the total distance of our trip is 2D, and the time we spent is just D over 70 plus D over 50. I'm just going to get a common denominator in the denominator. And now I've got a complex fraction. I'll just multiply by the 70 and the 50. So now, since all this stuff is being multiplied, we can see that the distance cancels out. Like we observed previously, the distance doesn't matter. And then we multiply all this out, and I think it looks like we get 58 1/3. Which is less than 60. It makes sense that it's less than 60 because we're not finding the average of our speeds. We're finding the average speed. And we spent more time doing 50, and that brought the average down. We spent more time going 50 miles per hour, and that brought our average down. We spent more time going 50 miles per hour, and that brought our average down. D divided by 70 is going to be smaller than D divided by 50. You have 70 people and you split a treasure, they will each get less than when you have 50 people. In Ocean's 12, if the take was the same, the split would be smaller. I like in the Ocean's movies, the 11, 12, and then 13, and then they went to 8. That was a good idea. They saw what was happening in Fast and the Furious, and they're like, oh, the cast is getting too big. The cast is getting too big. The individual take is getting too small. Let's reset this and get rid of 5. Any questions? We're not finding the average of the speeds. We're finding a weighted average. And we spent more time doing 50. So the 50 counts more. It's like if we all vote on whether or not we're going to have a final exam. Each of you gets 1 vote. I get 41 votes. But we get to pretend that we're voting. Any questions? So that's an algebra way of thinking about it. That's the average. Thinking in terms of averages, the way we think about that. We don't just want to automatically average things. Originally, this was the Tina Turner song. But what's calculus got to do with it? What's concavity but a second derivative? And I go, let's punch this up a little bit, make it a little more accessible. Let's draw a graph of what was going on here. On the first part of our trip, we were going 70 miles per hour, and we did that for some amount of time. Yesterday, we said this is the average speed. We took acceleration out, and we made our velocity function flat. What is the area of this rectangle, given the setup we have in our algebra style? Well, this took a certain amount of time that we don't know. So we just said that the distance that we traveled was some amount, and we called that capital D. So this area is the distance, and that means this amount of time is whatever that distance is divided by 70. Then we drove back and we were only going 50 miles per hour. So our speed drops down to 50 miles per hour. Once again, we have taken acceleration out of it so that we could make these flat lines. Now, I can't do this for just the same amount of time, d over 70, because that will not be, we won't get back to where we started. What we need to have happen is that the distance needs to be the same. The area of these two rectangles needs to be the same. So I need to make this one longer to compensate. So I need, since the height of that rectangle is smaller, I need to make the width longer. Since the height on the second part of the trip is smaller, we need to make the width longer. So to get an equal area, we need to make the width longer. If we're looking at a graph of our speed, then the area under the curve will tell us the distance traveled. There's the total time that it took, d over 70 plus d over 50. And then the total distance is 2d. How's everybody okay? I just realized I made these two areas like the orange and blue, so I use Mets colors. Yeah. I don't know if the Mets still use orange and blue. Teams tend to like decide that there are some cool colors that would be cooler for them to use, so they start like a lot of uniforms, they start using black. Anyone know why the Mets colors are orange and blue? So baseball history, the Giants and the Dodgers used to both be in New York. It was the Brooklyn Dodgers and the New York Giants. Then the Dodgers came out west and the Giants came out west, leaving no National League team in New York. New York finds this unacceptable because New York is like the center of the universe, according to New York. And also, baseball's greatest rivalry left town, and New York wasn't having any of it. So they say, we need to bring National League baseball back to New York. And so the Mets create a team called the Mets. And then they, as in my opinion, they do the Mets just super dirty. It's like, all your team colors are going to be orange and blue because you're not going to be your own team. You're going to be there to remind us of the teams that left. That's fucked up. That's like getting a divorce and then naming your kids after your ex. It's like, oh, wow. You need that reminder of the teams that left you, right? The teams that they left. They're like, oh, bye, New York. We're out of here. And we're taking our cool rivalry with us. And then they're like, oh, let's pretend that there's a rivalry with Boston. And so that one was invented. Well, we got to have National League team because we're New York and we have to have everything. So anyway. Never sat right with me that the Mets were like orange and blue. And I knew why. I'm like, well, what's bothering me about this? And then finally one day it hit me. It's like, oh, they wanted a reminder of their ex. It's like getting married and they still keep pictures of their ex around. Like, well, no, it's just, like it's just part of my history, so I gotta keep it up there. But New York, you have issues, is what I'm saying. New York, you have issues, seek therapy. Stop trying to be the center of the universe. You're not the main character. Incidentally, I have the same message for San Francisco. Like San Francisco's be like, oh, in San Francisco, it's so awesome, so wonderful. It's like, is it even a second-rate city? I mean, anyway. Anyway, what are we talking about? Oh, yeah. Any questions? Comments? Snide remark? You're hanging around in San Francisco, I want you to think about all the dead people that are still buried there, even though you can't bury the people there anymore. They used to bury people in San Francisco, and then they started moving. When they moved a lot of them to Colma, they didn't move all of them to Colma. And still, when you do construction in San Francisco, sometimes you just find bodies. I learned about this yesterday. I'm like, there's like cemeteries that we kind of forgot about, that we never moved. And so every once in a while, bodies just show up. Any questions on averages anyway? Now, what we saw here we have some calculus thinking. I took this velocity, these speeds actually, took these speeds, and I found the area under them to be the distance traveled. And we used that to find the time, and that brought down our average speed. The idea was we had a weighted average. It wasn't equal amounts of 70 and 50. It wasn't equal amounts of 70 and 50. There was more 50-mile-per-hour going on than there was 70 miles per hour. It was a weighted average. So we want to think more about average and more about calculus. And we want to talk about the average value of a function. When we're finding an average, we're thinking of it in terms of a density. How much stuff is there, divide by how much space it takes up. We're thinking of it like a density. How much stuff is there, divide by how much space it takes up. Now, we think about this by adding up all the values and then dividing by the number of values. You just add up all the values and divide by the number of values. Add up all of your test scores, divide by the number of test scores. But what if we're not adding up a discrete set? We don't have a discrete sum. What if we don't have a discrete sum? What if we don't have a discrete sum or a number of things? How do we add things up? The same way we always add things up when we're trying to add up over a continuum. We just do a definite integral. A definite integral is going to be our continuous sum. The definite integral takes place over an interval. The length of the interval is how much space those values take up. So that's our number of things. So we're doing the same thing. We're just modifying it. And since we don't have a discrete sum, where we have all these pluses in between all the different values, divide by the number of values, we integrate. We find the definite integral for our total of the values. And since there's not a discrete sum of things, we just divide by the length of the interval. So the average value of a function on an interval from a to b is going to be the total, the definite integral. Here we are adding up all the values of the function from a to b. And then we'll divide by the number of things that we have. Divide by the length of the interval. That's the average value. That's how we're thinking about it. We're thinking about the definite integral from a to b as adding up all the values of the function from a to b. And then for the number of things, we just divide by the length of the interval. If we think about this in terms of area, the definite integral from a to b of f of x to x is the area under the curve and above the interval. So that's our total area. Down along the bottom, b minus a, that's our length. And so if we say, let's draw a picture. So the average value is the area, the definite integral, divided by the length or the width of the interval. So what we're thinking of is some value that if we make flat the function, we get the same area. Area is equal to length times width. So length is area divided by width. Average value is how much stuff is there divided by how much space it takes up. The definite integral is saying how much stuff is there. The length of the interval is saying how much space it takes up. When we say things like our average speed was 70 miles per hour, we're taking the total distance that we traveled, which is the area under some continuously changing function as our speed continuously changes, and calculating the area under the curve. That's the distance that we traveled. We don't actually have to calculate it. We just measure it with our odometer. And then we measure the distance, the time it took us to do the change in time by looking at our watch. Actually, I'm wearing a watch today, but I don't normally. By looking at our phone. And then we get an area that's the same amount. We figure out the height to give us an equal area. So the area of this green rectangle is the same as the orange funky area under the curve. Any questions? We want to see how all these ideas are connected. The ideas of average, why we calculate the average value of a function this way. And we want to see how this is connected geometrically to area under the curve. Any questions? How's everybody okay? I took my glasses off, so it's hard to tell. It's also when I'm writing stuff down here, I have to get so close to the paper, so I can't see it otherwise. Now, if I had longer arms, it wouldn't be a problem. Or if my eyes were younger and just were bad at far away, but now they're bad at everything. So I can't do both at once. At one point, I was thinking it would be kind of convenient if I could do like Plastic Man or Reed Richards and just make my arm longer so I could write down at a distance that I could see. But if I was like Plastic Man or Reed Richards, I would just change the shape of my eyeball so I could see better. That one took me a long time to come up with because took a long time to start thinking about root causes of things. So any questions? Comments? Snide remarks. Now, here's the tricky thing. Here's the sneaky thing that I'm going to do. I'm going to give you a table of values. I'm going to give you a table of values. I'm going to give you a table of values and ask for the average value of the function. This is a trap. I'm saying, what's the average value of this function? And you're going to find the average of the values that you know of this function. What's sneaky here is that the function I gave you is not linear. The function that I gave you is concave down. This is a trap to see if you'll just find the average of the values. And not the average value. If I really wanted to be sneaky, I'd say, what's the average value of g of x? And if I really wanted to be nasty about it, I would make problem one average value of g of x. And I would have the computer check it. So you would know right away, if you find the average of the values, it would pop out the correct answer. It'd say, oh, yes, that's correct. You are correct. The average value looks like 60. But why is the average value of f of x not 60? So that would be a fun question. How's that, okay? And then after you get that wrong, you'll be like, "I'll explain why you got that wrong." Any questions? So remember, the point is not find the average value of the function. I'm fully confident that everybody would be eventually able to calculate that if I just told you how to calculate it, because I just told you how to calculate it. This combined with our approximating definite integrals work, you can just find the definite integral from 0 to 12 of f of x using the methods that we have. You use Simpson's rule, would be the closest to the actual value. And then you just divide by 12 the amount of space we're taking up, the length of the interval. Fully confident that you all could do a Simpson's rule, divide that by 12, and report the answer. The question is, why is that value not the average of these values? I didn't make the average of those values 60, did I? Why is it not just 100 plus 90 plus 70 plus 40 divided by 5? Any questions? Comments? Snide remark? All right, that'll be your question for today. Think about not how we could get the average at the average value of the function, because we know we could do that. Definite integral, use Simpson's rule. That would be the closest to the actual value, since we have a limited set of information. It would also be kind of fewer calculations because you could do midpoint 2, trapezoidal 2, find the weighted average. Why is the average of the values okay for g of x, but not okay for f of x? That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day. And thanks for playing.